Let's go over our assignment real quick. And our assignment is we are given an 8x8 grid, and we are given an input of 63 characters, which consist of down, up, left, right, or asterisks, which can be any of the previous moves. And the goal of this assignment is we start at the top left and then we end at the bottom left, and we have to reach the end while traversing every single cell and then find the number of paths possible with the input. For this assignment, we're given two cases which we're going to use to show our demo. First, we're going to do case 2 since this is a faster path, and it's a 186 millisecond runtime. And now we're going to move on to our full case 1 where it's a full asterisks. This is going to take a bit to run, so I'm going to talk about our brute force code and how it works in general. So first, this calculate path is just to verify the input and outputs the total paths and the runtime. And we have this part of the code where it processes the input characters. And let's move over to our main way the code works. So find total paths, this code basically checks for every character. If the character is asterisk, it's gonna branch out and recursively run through every branch of the directions, and if it's just a directional command, it's gonna move up to the direction of the vector. Then for every cell visited, it has a bit mask, and it's gonna change itself to visited state. And then once all the characters that ran through, it's gonna check if the ending cell is matching the bottom left where it's set here. And there's also backtracking, where this code mainly prevents us from having to recalculate already traversed paths. And as you can see, this is the output for the full asterisk. It's 36 seconds. And this code, without any further pruning or optimization, would have been 4 to the power of 63.
So this is the initialization step of our program. So the step is crucial because it ensures the pathfinding process is efficient. So before performing all the pre-calculation, a few variables needs to be initialized. Right after that, we can start the neighbor pre-computations. So here we determine the valid neighbors for each cells in the grid. For example, a cell in the middle will have 4 different neighbors. And to optimize the process, we store the neighbors of each cells using bitmask. For example, we have to flatten the 2D array into the 1D array and represent the index of each cells from 0 to 63. So for example, at index 0, this cell is next to cell 1 and cell 8. And we will perform the bit manipulation here and store it into that specific cells. This method will have the time complexity of big O m power square. Right after that, we will perform the connected cells precomputations, or the heat map. This precomputation is similar to the previous method. We calculate the number of neighbors next to a specific cells, and this represents the number of possible paths when we are at that cells. For example, at the edge of the cells, there will be 2 different neighbors, and that indicates we can only go to 2 different directions. We are at that edge, and we were at the middle. It will be connected to 4 different neighbors, meaning that when we're at that cells, we can have 4 possible paths. And this method will have the time complexity of n squared 2. Finally, this is the eliminated functions. This function will calculate the shortest distance from a given cells to the target cells. And the reason that is eliminated will be mentioned later on.
This method verifies if the path follows the Manhattan algorithm by comparing the remaining step with distance to target. Typically, it helps to prune around 3.5 million invalid paths, help lowering the search time. However, this method is outperformed by the other pruning methods, so is not included in the final submission. MaxStep has this formula. This output of this method is assigned to the instant variable shortest distance to target. This is, for example, current cell in this position, distance to target is illustrated. Current index has this formula, which is equal to 1 for now. Remaining step has this formula, which is equal to 62 for now. Distance to target equal to 8. Basically, this line accesses the precompute value at the current index. The program keeps exploring the path because the output is true. Final example, current cell is here. Remaining step is 3. Distance to target is 5. The program stops because the output is false. The time complexity of this method is bigger of 1 because it performs a fixed number of constant time operations, including symbol calculation and array access. Now come to is that and methods. Some notes here. Left and right refer to the cell adjacent to the left and right of the current cells respectively. Up and down refer to the cell directly above and below the current cell respectively. Visited cell equal to 0 means it is visited. The method begins by checking whether the neighbor cells around the current cell are blocked. Left checks if the left neighbor is either out of bounds or already visited. Right does the same. Up and down check the neighbors directly above or below and below respectively. Horizontal block, that is true if both left and right neighbors are blocked, and while up and down will remain open. Vertical blocked, this is similar logic compared to the horizontal block. Finally, the method returns true if either horizontal block or vertical blocked is true, otherwise it's false.
In contrast with the previous pruning method, can visit all remaining cells is utilized to determine the reachability of the current cell position when allocating into another unvisited cells within the grid through the implementations of a BFS traversal algorithm, which helps to find the shortest path to traverse. In our case, the method allows efficient connectivity check by leveraging the bit mask for neighbor checking and cell tracking. When looking into the logical flow, it can be further understood that the method first computes the numbers of remaining cells in the grid, as well as the starting index of the current cell position as a way for the system to keep track of all the important values. Continuing on, the method proceeds to initialize the BFS state, where several values are set up, including visited mass, start mass, inverted visited, reach, and frontier. All these values are initiated beforehand in order to prepare for the BFS algorithm. When performing the BFS, the method first retrieves the valid neighbors for each cells in the current frontier using the pre-compute bitmask. Likewise, it will also store the reachable neighbors into the reach and then update the next frontier. The loop will continue to operate until the entire reachable region on the grid map is explored and will stop when there's nothing left. From here, the method will proceed to count the numbers of reachable cells in the reach and then compare between the remaining cells and the reachable cells. If the reachable counts match with the remaining cells, then it will return a true statement, or otherwise it will return a false statement if it doesn't match with the count or the start cell has already been visited. Overall, the application logic of the method can be quickly inspected through the benefits and drawbacks. While the method is very time consuming and offers very diminishing returns, it still ensures efficiency and performance improvements while avoiding dead end and wrong paths. Because of this, the time complexity of the method can be represented as OV, with V equals to the numbers of cells in the grid.
So, alright, I'm gonna talk about the two methods with the algorithm. So first is the border check and the prioritized single connection cell. So first thing is the border check. We realized that in order to make a path, we have to follow this border patterns, where you have to reach these cells in order, like, follow the arrows right here. So for example, in this image, this is a dead end because it split the grid into two halves. So to solve this problem, we have to follow that. We need to reach this before we reach this or this. Yeah. we have to follow the pattern, or else it is invalid move. So to check this, we check if the current position is at the border, and depending on the border, we check in the pattern. For example, if we reach the bottom cell, we will check the right cells. If this is not visited, we return false. And next one is prioritize cells with one connection. So as you can see in the image, when we reach this position, this cell has one connection left, which means that if we don't move to that, for example, we move left, when we reach it again, it's gonna be a dead end. So to early check this, we make a heat map where each cell represents its connections. So this cell has one connection, so we have to move there in order to not making a dead end. And we do this by making the heat map, and we check every move if it is one or not. If it's one, we only move to that direction. And about the result, the final time is around 40 seconds, and if we don't have the border constraint, it's gonna get up to 250, which means the border constraint improve the process, the time, by five times, and the heat map improved the time by 3 times, 151 compared to 40. And that's the final methods of our algorithm. Thank you for listening.